From Photonics Media, this is the podcast that takes listeners inside the physical science of light as we explore groundbreaking and industry-shaping progress in lasers, optics, imaging, metrology, and sensing. Each episode, our hosts welcome optics and photonics luminaries, rising stars, and market leaders for robust discussion about the trends shaping the field of photonics. From research and development to commercial innovation, we're on the air for unparalleled insight, offered on All Things Photonics. All Things Photonics is brought to you by PolyScience and Lumencore.
Today's episode is brought to you by PolyScience. For over 60 years, the PolyScience line of award-winning temperature control equipment has been helping the photonics industry reach its goals safely and efficiently. Our products are made in America and delivered globally. Please visit polyscience.com to learn how we can help you. Changing the world of chillers is more than a tagline. It's part of our history. Today's episode is also brought to you by Lumencore. Lumencore excels in the manufacture of technical lighting, scanners and imagers, and metrology. Visit us at lumencore.com to see how we can best support your new products and OEM production.
Our interest in our first guest today is one that has existed for some time, and if you've followed his work, it's easy to understand why. The Zubin Jacob Research Lab at Purdue University, led, as you may have guessed, by Professor Zubin Jacob, is producing work that is revolutionizing thermal imaging, unraveling picoscale properties of optical materials, solving mysteries in quantum photonics, and even more if you can believe it. Our conversation with Zubin Jacob covers a lot of ground, and yet it barely scratches the surface in the depth of work coming out of his lab. In the first portion of today's episode, we speak with Jacob about his lab's recent work in thermal imaging and the impact that the work could hold for LiDAR, radar, and sonar detection. The conversation also touches on Jacob's work in quantum, with a quick primer on the subject before delving into his work with topology and spin qubits. Today we also hear from TRAQC, recent winners of the 2024 SPIE Startup Challenge, the company's terahertz light-enabled solution, and senior editor Jake Saltzman in the second half of today's episode. Up next, though, we hear from Joel Williams and Zubin Jacob, the Elmore Professor of Electrical and Computer Engineering at Purdue University.
It's sort of difficult to pick a place to start, but I think I'd like to start by talking about HADAR, standing for Heat Assisted Detection and Ranging. That one generated a bit of buzz, an invited talk at the Materials Research Society's meeting in Boston, and a presentation at the ORC seminar series last year. For the folks in our audience who might not be familiar with work, could you give us just a quick rundown of the technology and how it works?
Sure thing. Thanks, Joel. So HADAR, as you said, stands for Heat Assisted Detection and Ranging. And you should think of it as a machine perception approach. So we want to understand our surroundings, and we'd like to do that with equal accuracy at daytime and nighttime, right? So we have to be able to use other modalities than, say, just visible perception to be able to work as well in the day and night. And it turns out that all objects at non-zero temperatures, they actually emit thermal radiation. So what that means is that we are constantly kind of sending off information about us, and every single object is actually doing the same thing, even in the nighttime. And now you can use that heat radiation to understand your surroundings, to classify objects, and in other words, do perception for machines, both in the day and night with equal accuracy if you actually use this thermal radiation at nighttime. So in a nutshell, heat-assisted detection and ranging is basically using these thermal signals to provide more situational awareness about a scene.
Excellent. Now, when we first covered that advance in our research news on the website, one of the details that really struck me was that it could have an impact on par with LiDAR, sonar, and radar. Could you tell us a little bit more about the technology's potential, specifically what it means to overcome the ghosting effect in thermal imaging?
Great. So no, that's a really good question, and kind of thank you for bringing that up. So that's really the vision of the work. I mean, where we are headed is really to make it a technology that is as ubiquitous as, say, LiDAR, sonar, and radar, right? So these kind of approaches or to detection and ranging, they're really based on, let's say, some sort of wave physics. That's, for example, the radar really means it's radio waves, or microwave going and hitting some objects and then coming back to your detector, and then you are able to get some understanding about the range, how far is it moving away from you or is it coming close to you, and some more details, right? So that's how radar works. LiDAR is kind of laser based, so it's basically a laser pulse. That's going and hitting say the object of interest and again comes back to your detector. And sonar really stands for sound waves doing the same thing. Now, it turns out that having complementary modalities for such detection and ranging can be really important, especially for this nighttime navigation. Now, each of the approaches that I mentioned, they have their strengths and weaknesses. So one of the other kind of components and modalities that we are adding is to use heat waves, heat radiation, to achieve this detection and ranging. It's a completely complementary way of looking at this detection and ranging problem. So we think that all of these techniques could work together someday to actually get the maximal amount of information from a scene with all the different kind of objects which could be moving in the day or in the night by using HADAR. So that's kind of how all these sensing modalities work. The underlying theme is wave physics, but the different waves carry very different information, and it's best to actually exploit all of them together. And the heat waves, which is thermal radiation, that's specific to HADAR. Now, having said that, we should also acknowledge the fact that, thermal imaging as a kind of approach for sensing at night does have a long history. So that's something that has been developed over many decades. But it turns out there are some really critical roadblocks in taking thermal images and getting the accuracy at the level that you would need to conduct HADAR, like basically detection and ranging with a high accuracy. And that roadblock is very colloquially called ghosting. So some of you, especially our kind of audience, may have seen thermal images, right? If you take a quick look, or if you just Google thermal images, you'll see a lot of pictures and it looks like you've seen a ghost. If you look at a person's face or you look at kind of objects, it seems like you've seen a ghost. And that's one of the reasons that people use thermal imaging to maybe augment certain existing sensing approaches, but it's never been able to really go to the accuracy needed for detection and ranging. And the reason this ghosting occurs is because of the fact that all objects in a scene, not just the ones that are of interest, but every single one in the scene is constantly emitting thermal radiation. And that actually scatters off your object of interest and then reaches your sensor. So it's a really convoluted mix of information that is reaching your sensor. And to actually make sense of it, you have to overcome ghosting. And you need to get texture and contrast in your image to be able to do detection and ranging. And that's what HADAR does. It actually overcomes this texture limitation and provides accuracies which are 10 to 100 times better than if you just use thermal imaging by itself.
Excellent. So in prepping for this interview, one of the first things that I did was search your name on our website. And one of the more recent works of yours that we covered was a paper that you and your group had published in Optica about a compact thermal imaging system created with spinning metasurfaces. Could you give us a brief overview of that work? One of the things that I'm curious about, being, so maybe like a level or two above layman, is the spinning aspect of it, as well as how computational imaging comes into play to extract the thermal information.
Great. All right. Well, thank you so much once again for covering the work. We're very happy about the attention that it has received, and a lot of questions that we've been getting from a lot of interested industry, kind of academia, as well as government. Now, so I'll give you a bird's eye view first, is that, if you go and look at the thermal imagers that are available today, many of them, they do not give you the spectral information. And spectral information, think of this as, if you take a image in the visible spectrum, you really rely on the red, green, blue colors to give you context. And this is true about machine learning algorithms as well. The RGB colors are very important in the visible spectrum. And it's actually very easy to just go to the market and buy a webcam, and I mean $100, and you get a really good image which is RGB. Now, the same thing really does not exist in the infrared spectrum, which is where heat radiation is emitted. And over there, it's basically, think of it as invisible radiation, but we want to effectively get those colors in that spectral range as well. And that's very challenging to do today in a compact form factor. So what we've done in our Optica paper is provide an approach to get this spectral information in a compact form factor camera. So we have some special modules, spectral modules, that actually consist of metasurfaces. So it's thermal or infrared metasurfaces. It's just a structured, textured electromagnetic surface that scatters the incoming thermal radiation in a special way. Now, then what we do is that we do the computational imaging and the post-processing to extract out the colors. So there's one very key aspect that you mentioned, and we also put that in the title, was the spinning aspect of these kind of special nanostructured surfaces. And it turns out that, we require diversity of information at the sensor. So you're really trying to collect a few colors, but we want to collect probably like 10 to 20 different spectral bands, not just 3. 3 ends up being not sufficient. So we need like 20 kind of spectral bands, and we need to be able to label them 1, 2, 3, 4 up to say 20. Now, quite often, previously people had thought about kind of lateral motion to just scan through these colors, known as push broom technology. So you kind of scan through the colors after a scattering medium and try to collect one color at a time. But this ends up being slow, and the lateral motion is also rather sensitive to kind of vibrations and stuff. So the key kind of idea that we developed was that, instead of this lateral motion, which was known, let's actually think about a spinning motion of this metasurface and use that to collect different colors. So think about it as different rotation angles will give rise to some information corresponding to different colors. Yeah. So the other quick final thing that I'd like to mention is that some of the research that we're doing, earlier on we were talking about ghosting, machine learning. So that's a lot to do with the algorithms and signal processing. But some of the things that we just talked about related to the Optica paper, that's to do with, say, resource-constrained computations in an edge environment. So that's more, say, computer engineering. And the previous thing was much more signal processing. And at the end of the day, when we bring in the thermal physics, that's when we can actually constrain the dimensionality and really get images. So it's really bringing in together kind of physical design, computer engineering, as well as signal processing, which are all ECE, like electrical and computer engineering core areas, but fitting it in a very unique way to solve some edge perception problems.
Excellent. Of course, given that it was published so recently, it's probably still a little bit early, but how is that work how is that work progressing? What do you and your team plan to explore next on that?
Sure. Yeah. I would say it's progressing well. We always want to kind of progress faster, but that's just how the things are. It's always challenging. There's like multitudes of new challenges that come up every day. But then we're committed to really getting this into the hands of the people, hopefully sooner than later. And I'd say that right now, some of the challenges that we are working on is definitely a compact form factor. I think this is very crucial at the end of the day for technology adoption. And we also want to overcome the requirements for cooling. Now, it turns out that because of the infrared spectrum, the radiation carries less energy, and you actually have to cool some of the detectors to get good images. So we're overcoming this cooling requirement. We don't want a fridge with the camera. And so that's the second kind of challenge we are overcoming. And the third one, as I mentioned, is this processing this information on the edge. And I think there are lots of interesting kind of algorithmic advances with the physics baked in that needs to be developed to actually execute this entire system and make it work in real time.
Awesome.
So hopefully the next time we talk, I have a live demo to show you.
That would be excellent.
Yeah.
I'd love to see it. Yeah.
Great.
So switching gears a little bit, I'd like to explore some of your work in the quantum domain. Maybe a good place to start with that would be an article that you had published in 2020 titled Recent Advances in 2D, 3D, and Higher Order Topological Photonics. A little bit of inside baseball here, but when I'm doing my morning searches for news, whenever I see an article with that title, Recent Advances in blank, I always like to print it out and save it to read it later because we cover a lot of technologies, so it's always nice when I find something like that that can give me sort of a roundup.
Right.
And sort of in the same way, we have a lot of folks listening in from different areas of the photonics landscape who are certainly hearing a lot about quantum photonics, but might not really be up to speed. So for those of us who are, sort of in the dark about quantum photonics, could you give us some of the big picture aspects of the field, which, of course, is a huge question.
Yeah.
Maybe a little bit more specifically, what is your lab working on, and how does it tie into that 2020 article, if it does?
Okay, sure thing. So I'll give you a bird's eye view first, and then we'll go to a little bit of the details of what my lab does and so forth. So the bird's eye view that you want to think about is that the radiation that we are generally used to, say coming from the sunlight or coming from a laser pointer, this type of radiation can be understood to a large extent, not every single aspect, but to a large extent with the laws of classical electromagnetic radiation, right? But it turns out that, if you actually go to understand the basic building block of light, like what is the basic building block? It actually consists of a photon. And think of it as kind of the smallest building block, energetic building block of electromagnetic radiation. Now, over many years, we've now understood kind of the behavior of photons very well. And to some extent, we know how to generate those single photons. We know how to detect these single photons. And in between the source and the detector, we know how to manipulate them as well. But it turns out that, to be able to actually execute, say, advanced computations or, say, edge processing or some sort of algorithmic advances using these photons, it's very challenging. You require your engineering of the source to have extremely high purity, the detection accuracy and the detection efficiency to be 99.99%, and no loss of the photons inside your engineered structure either. So very quickly, something that we understand well, as soon as you want to build a technology, there are many engineering challenges to be overcome to really get there. So what the community is doing overall is, one of the challenges is building just better sources of photons and with special properties on demand and with high fidelity. That's one of those overarching challenges for the research community. The other is, of course, new classes of detectors that can actually sense this light and the various properties at very low levels, like extremely low photons. Think of them as I'd say kind of in terms of energy, at least like 8 or 9 orders of magnitude lesser than kind of what you would be used to in the classical domain, right? So, and I think, say, compared to what happens in optical communication systems. So now at this level, you need new materials, you need to overcome cooling. So there are many subtle aspects that need to be taken care of to actually achieve this engineering. And then finally, you need building blocks to change the color of the photon, to maybe get 2 photons to talk to each other. All of these small building blocks have to come together. And at a high level, you can think of it like a photonic integrated circuit that would work in the quantum domain. That's one of those big goals that many groups are after. Now, in my group, what we are focusing on is a little bit on the fundamental side of light-matter interaction. So it just turns out that light by itself does not like to interact with light. It's just how it works. But if you have matter, the light interacts very strongly with matter, and it can indirectly interact with light again, or you can actually control various fundamental properties of the photon itself. So in that article, the recent progress in topological photonics, what we are really trying to get to is first giving an overview of what the field is trying to do, coming up with very clever designs for controlling light, getting maybe light to move one way and not the other way. And then finally, my group is trying to work out some quantum theories of light-matter interaction so that we can start understanding, what happens to the photon when it passes through a material. So really what happens to the microscopics, and we like to think of it almost like picoscopics, because microscopics was a word that was used 100 years back when there was just the microscope came out, or they didn't know what the microscope could do. But now we know that, we understand everything very well at the microscopic level, even at the nanoscopic level, but below the nanoscopic level is where some really interesting light-matter interaction occurs, which are completely quantum in its behavior. So that's of a lot of interest to my research group.
Excellent.
Yeah, that was a long answer, but I hope I did cover all the points that you had in your question.
No, certainly. That definitely helps. Give a sort of a primer on the subject.
Great.
And I guess sticking with quantum, I'd like to ask about spin qubits. There's of course a lot going on with quantum computing, and we're still at a stage where everything's still kind of up in the air in terms of what type of approach is going to win out. Of course, us being in the photonics field, we're all rooting for the photonics approach, or, at minimum trapped ion, because, it still utilizes lasers. Could you tell us a little bit about what makes the use of photons as qubits advantageous over other approaches? And, what attracted you to spin qubits?
Great. So, like you mentioned, and very correctly so, that there are multiple different qubit technologies and platforms that are being pursued by both industry and academia, and it remains to be seen which one is going to win. But at the same time, we also know that as far as really communicating between quantum systems goes, photons are the best mediator of this quantum information between nodes, distant nodes, or closely spaced nodes. So that's very clear to the community. So photons have that advantage in terms of being a flying qubit. Take information from here and relay it to, say, another quantum system. And there's a lot of research going on about that. But there are also groups that are working on, if this is going to relay information, why don't we actually make it do some small amount of processing in nodes as well, so that it can interface to the quantum system better. So this is a level of processing which is possible with photons, but like I mentioned, photons are kind of very notorious in the sense of they don't want to talk to each other. Unlike, say, 2 charged objects, they are already interacting. Like through 2 electrons, they do have very strong interactions because of the charge-charge repulsion, right? So photons don't have that, so they don't really interact very strongly, and you have to do a lot of engineering to get that interaction to occur. So those are the pros and cons of the photonics approach. And now in terms of spin qubits, now it turns out there is a class of spin qubits which are optically addressable. So there are kind of similarities with the ion trap system there, that you can actually definitely read it out optically, say the quantum state of a spin qubit. And you could also get the qubit prepared in some state using light. So it was natural for us to look into those spin qubits, which have these nice optical addressability and optical readout, which is why we got attracted to spin qubits. And these are known as also known as quantum impurities, because they also occur naturally in many solid state materials. So in that sense, they are easy to work with. But of course, there are separate challenges of getting ordered arrays that can actually be used for computing.
At Photonics West earlier this winter, the team from Montreal-based TRAQC, TRAQC, took first prize in the 2024 SPIE Startup Challenge. The McGill University Spinout's real-time automated inspection solution for printed and additive electronics earned the company a first-place finish and a $10,000 award. The terahertz light-enabled solution monitors the fabrication of next-generation devices with high speed and precision. The technology aims to reduce costs in fabrication, leveraging photonics technology to spur innovation in electronics manufacturing. The terahertz domain is well known and widely regarded for its use in non-destructive testing, and it lies at the heart of TRAQC's solution. The team of Mariia Zhuldybina and Benjamin Dringoli know well that the key to harnessing the terahertz band is bringing a solution out of the lab and into industrial settings. For the benefit of the future of the additive electronics sector, that is exactly what TRAQC has done. Post Photonics West, we caught up with Mariia and Ben as TRAQC eyes its pilot rollout. I want to begin, and again, this is sort of year 3 of our ability to host the SPIE Startup Challenge winners. We're very privileged to be joined by Ben and Mariia from TRAQC. This year, every year, a little different. We'll be talking about automated inspection and the mechanisms and ways in which that is done as we get into our conversation here today. I know there's a story to be told here about electrical engineering and electronics, and it occurs to me that automated inspection in real time for printed and additive manufactured electronics is kind of a very logical way to bring photonics into the world of electronics. Not the only way, but a very logical application. With that in mind, if you care to share the origin story for TRAQC, our audience would love to hear it.
So probably it's me who will start. And the TRAQC was born during my PhD, which I have done at École de Technologie Supérieure in Montreal, Quebec, Canada, under the supervision of François Blanchard. And at the beginning of my PhD, the goal was to find a way to do quality assurance for printable electronics using terahertz lights. How to do it, what to do it, we didn't know exactly what. And then, is it bothering the noise which is coming from the messages? Or it's okay?
It's probably not a problem. If there is a way to get rid of it, though, it probably wouldn't hurt.
Okay, I closed the mail, but the Teams doesn't, I can't close it. Sorry. So, François Blanchard. Yes. Okay, I say about the goal. And also during my PhD, I had a chance to go to one of our collaborators, which is Technology Transfer Center in Montreal, which is called Institute for Graphic Communication and Printability, which has huge production presses. And the idea was there to produce some samples for testing in the lab. And when I came there, I was fascinated by the size of the printing press, by the production it's capable to do. But when I was seeing people doing quality assurance, I was like, wow, it doesn't match these two worlds, you know? And I was thinking at that moment, I was like, I would love to bring my research to the real production, real life. And it was just a thinking. It was back to 2017, 2018. And then when it started, like I started doing more experiments and so the need about this quality control, I decided that, okay, maybe I can try to do a startup. And luckily, I we went for a beer with our two research groups, with mine, with François Blanchard, and Ben in his group is supervised by Professor David Cook in McGill. And I said to Ben, because we took class before together in McGill, and I said to him, you know what, I want to do a startup company. And he said, okay, give me elevator pitch, what you want to do. And I just explained him what's the idea. And luckily for me, he jumped on this boat, and we still continue doing it together and trying to bring this solution to the real life.
You got to jump in, Ben. I know that we're talking about the bridge between additive electronics and the manufacturing side of that technology area, and then automated inspection, which is a different but very related technology area.
I'm sorry, I didn't catch your question on that.
Oh no, just inviting you to jump in on the sort of the pursuit to bridge these two technology areas.
Okay. Yeah, I think you're right in that it makes a lot of sense. We've seen a lot of advancement, particularly with imaging solutions as they've become applied to industrial manufacturing. And that's something that we wanted to kind of be inspired by, to say, hey, there are definite ways that optics and photonics can really benefit these industries. But to take our experience and to try to simplify the measurement down as much as possible and create something that's not only easy to use, but quite flexible in its application that can serve multiple modalities. I really think that let's say the flexibility of light and the flexibility of these flexible electronics really do make a really good match in the ability to create a process control tool that, has many different features and provides value on many different fronts.
Non-destructive testing and I suppose inspection as well within that is really sort of goes hand in hand with terahertz light when we talk about the terahertz band. But these solutions that terahertz enables are not principally targeting additive electronics or even system components, right? These solutions are, as a result, not always able to exist outside of a laboratory setting. What has TRAQC identified as the market opportunity for its solution, insofar as it relates to the very distinctive and nonlinear terahertz roadmap?
Mariia, that's yours.
Can you repeat the question? Sorry,
A lot of the conversations that we have when we talk about terahertz, first of all, it's about the terahertz gap and that phrasing, but it's also about non-destructive testing and whether it's real time or not. That's a major focus of terahertz applications. But a lot of these terahertz solutions are not yet able to exist outside of the laboratory setting, and that really obviously restricts their real world application. So I'm just curious how TRAQC has, how it views its market opportunity for its solution, given that terahertz technology is somewhat complicated in that regard.
Just give me a second. I'm trying to formulate my words.
I think a simpler way to phrase that question is terahertz is complicated, right? That roadmap is not fully established yet, but it's obviously a major part of what you do. So just that relationship between being a startup company, but also using technology that does not have its own fully formed roadmap yet.
Yes. So our idea of the using like terahertz, as you say, it's very well known in the lab scale testing for non-destructive testing, and usually with imaging, as Ben was mentioning before. In our case, the solution which was developed is quite different. So we don't need to use imaging, first of all, which is already reduced the level of complication. And second of all, it's 1D measurements, we can say. We're simply extracting the signal. It can be the transmission reflection, and we can help with that for the production line in the printable electronics. So how we do it, we print metamaterials on the side of the production line, and with terahertz light, by reading the response of metamaterials, we can judge about the process itself, what's going on with the production line. So that's why
No, go ahead.
So that's why the level of the complication of terahertz goes down in this case, because of this is very unique solution. And second of all, yes, being a startup and bringing terahertz, since you understand the technology very well, it's really challenging. That's why we have a lot of, I would say, delays in our development. I always say we would like to go faster and develop faster, but there are a lot of uncertainties which comes up in each stage. which makes it challenging in terms of the technology as well, in terms of terahertz use. And it's terahertz has been going outside of the lab for various applications, but it's still not very well known as any other type of light we can see every day in daily applications.
I think that's absolutely true. And since you've brought up metamaterials, and certainly we're talking about terahertz light, this is somewhat of a sophisticated technology, despite your claim to be simplifying the mechanism. What exactly is TRAQC offering its customers? Because on the one hand, it's a solution. On another, it's very much a product.
Yeah, and I see that comparison. We see TRAQC's greatest utility as being kind of a central hub for the process control. There is a lot of, let's say, nice physics and, Mariia's blood, sweat, and tears through her PhD through that measurement method, but it's all in service of the goal of making the job for the managers and the line staff as simple as possible. So instead of having an advanced terahertz imaging system where people have to recognize defects and go through advanced software, we tried to have the metasurfaces and the laser do the analysis work for them and provide them with very simple, easy to read and easy to act upon guidance. We're continuously monitoring all the key parameters like conductivity and trace width. And since all the processes of this manufacturing are in service of keeping that standard, and that standard is what's being logged and automatically adjusted by the TRAQC system, we really believe that it is offering really a solution to a problem that hasn't been addressed yet. And whether the issues are changing environmental conditions that affect the drying time of the ink, or if the ink is too little or too viscous, TRAQC allows for these issues to be caught before the end of the job. And we think that benefit in material savings in moving from a very manual-based kind of labor and human-based analysis method to something that inherits the benefits of this continuous production method will be a huge change, and will hopefully, down the line, show folks how beneficial it can be to really do that hard work of taking this technology out of the lab and questing to make it, really matter for a lot of people whose boots are on the ground, making the stuff that we want to have in our pockets in the next 5 to 10 years.
I think that segues very nicely into our next question. And now that we've gotten some of the very difficult technology out of the way, we can talk a little bit about the end use. And just purely through a photonics lens, like, it doesn't feel that long ago that we were wowed by the ability to put lasers into like additive manufactured components. Like, that still blows the minds of a lot of us here. When we're talking about additive electronics in these pocket size or smaller devices and components, I suspect that there's been quite a bit of learning done there too. And with this in mind, where do you see the opportunity to work in additive electronics and printed electronics? Because that seems like a particularly robust growth area.
I agree with you. So printable electronics is a kind of okay. Printable electronics, I believe it's our future with the modalities with the facilities of the producing these devices at the large scale, at large speed, and using like a small amount of materials. Like, that's why it's called additive, because we just use the materials which is needed. And this type of the technology can find the applications in various industries. It can be simply transportation cards, RFID tags, medical devices, is like, because they the devices which can easily adapt the human body shape, as well as Internet of Things, which is growing extremely fast right now. So all of these devices in near future, they will be printed. And as we see today, why we see the value in TRAQC, that one of the reasons why it's not there yet is the quality assurance. The volume didn't come up there yet that we have it in our pockets, is the lack of quality assurance, which will allow this development and this production to go faster and at the biggest scale.
I ask this question often because I'm fascinated by the diversity of responses that I get when I speak to younger and startup companies. The question I'm going to ask is, where has the greatest learning taken place? And that's certainly a question where the answer can fall in just learning how to operate as a business. It can be in the technology. It can be in both. And I think that applies well for TRAQC. So I'll frame it to you this way. Where have you done the most pure learning so far on this journey?
I think both Mariia and I would strongly agree that the business side is the strongest learning case for both of us. We're from the academic world. We've been doing laser science. That's where we're comfortable. And there's always things that we can learn. But in terms of really feeling like we had to build an understanding from square one, from the ground up, it was running the business. Me personally, I haven't worked in the private sector. And so a lot of these things about, how long does it take time things to do? How do you keep communication with someone? How do you keep a relationship between your business and this other business? All of the quantitative market research that, we have our own quantitative methods, but in the social sciences and the business world, that's a whole other ballgame. And so we've been very, very thankful, I think particularly to be located in Montreal, where there is a really robust startup scene and a lot of university adjacent incubators who are very well experienced in taking folks coming out of labs with a strong technical background and building up their business case such that they can really make something out of the stuff that they put in the lab. For me, it's been a huge confidence booster to just be able to say, not only can we kind of talk the talk on the technical side, but we can also start, speaking that language, and finding success in that space has been, one of the things that keeps us pushing on forward, because you need some of those. You need that drip feed of success. And we've been seeing it, and it's been intoxicating as someone who loves learning. In the same way as physics, this is another chance for us to demonstrate and show the skills that we've acquired.
And certainly, Ben, you did quite a bit of this at Photonics West as you presented and ultimately earned the SPIE Startup Challenge title. Take us inside some of these conversations, though, either with investors or customers or fellow scientists or other team members, because you're not just explaining the technology, it's new, but you're also sort of fleshing out a roadmap at the same time. How do those conversations often go?
I think that there's kind of a mix, depending on this, let's say, the positionality of the person I'm talking to. We've had a lot of great help from more established companies, either the venture arms of these established companies, or maybe the folks who are, they have their quality control division where they eat, breathe, and sleep this stuff. And so it's been really nice to see the degree to which people are willing to offer their time for young entrepreneurs. It's been very, I'm not going to say surprising, because I generally like to have faith in humanity, but overwhelmingly positive, the amount of, just raw information that we can get from people who have 20, 30 years of experience in this industry. And so that's why we love events like SPIE Photonics West and the Startup Challenge, the Startup Focus they put on there, because everyone in the industry is already in that room. And it gives us a forum to say, hey, here's where we're at. Take a look at our pitch, pick it apart, and please talk to us after so that we both can be better as a result of this interaction. And so for me, from the investment side, from the technological side, my colleagues over at McGill who see this stuff, kind of through the grapevine, it's so great to be able to have conversations with people all over the spectrum. And we're going to try to attend as many events as possible in the future, because we really see that's where stuff gets done. That's where those conversations happen.
I mentioned I was going to likely ask this question a few moments ago, and the time has come. Hard for us to talk about terahertz really ever without talking about the so-called terahertz gap that exists, either in mind or in reality. How does a company like yourself view that? Because I've asked this question, for example, of Mona Jarahi at UCLA, the Terahertz Optical Electronics Laboratory, and in the kindest way possible, she said, how do you view the terahertz gap?
Well, I think with the development, which is going on so efficiently in the academic world for the terahertz, I don't think we can call it still gap at this moment. Yes, probably we don't have its application of the outside of the lab that much, but we are one of the examples where it can go, and there are many examples which are already working right in the industrial space of human needs. That's why I honestly don't think we can still call terahertz gap being a gap.
I think that's a fair answer, and we have it on good authority now here as well. We'll end with this. What's the future hold for TRAQC?
So right now, our biggest focus is getting towards the first official pilot of the commercial TRAQC system. We did a lot of work validating our MVP and making a lot of key changes to make it as economic as possible, make it as retrofittable and easily integratable as possible, and to strongly update the software to give it a strong use case post-installation and provide value, over years and years of operation. The pilot's taking place with a local partner in Montreal around May of this year, and that's going to give us the key performance data we need to really start pushing in terms of sales and getting this into the hands of real users. What we found is that folks who do printing, they're tech people like us. They're results focused, they're numbers focused. And so to get our foot in the door, we really have to say, here's the benefits. Here's the data set of it on the line for 2 months straight, measuring all this stuff. And so once we have that, I really think we can capitalize on the strong interest, not only in technical advancement that is present in these facilities, but also the strong need of these line managers who see rolls and kilometers of material just go into the trash. So to this end, we're moving towards the pilot. We have a pre-seed funding round open that will really help us accelerate the rollout of those pilots and grow our team with full-time engineers to cover the holes that Mariia and I have in our knowledge to really support our first paying clients, get them as happy as possible, and hopefully move towards working with, greater organizations, whether that be standards organizations, to try to get something on the books in terms of creating a standard for this, or even distributors or the printer manufacturers that could really allow us to access a greater degree of this market. And even, if we're, when we're super successful, the adjacent markets, coatings, solar panels, displays, all of these we can assume will advance their manufacturing in a similar way of, let's say, rigid PCBs towards these flexible circuits.
Well, Ben and Mariia, it all sounds great, and congratulations on the success to date. Thank you so much for taking some time with us. Congratulations on all the success, and we'll talk again soon.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.